What's going on, guys? In this video we're going to be covering the statistical tests of multiple linear regression. So we're going to do a quick review of why we can even use these statistical tests. Then we're going to do some t-tests, confidence intervals. We're going to learn what an f-test is, what a partial f-test is, and then we're going to learn the problems of using R-squared with multiple linear regression. Quick review. So we learned last chapter that if we take a bunch of samples of y is equal to beta 0 plus beta 1x, and then we sum up all the parameter estimates, and then we divide by the number of samples, that this number will approach the true population parameter. And in doing so, each of these parameter estimates will ultimately form a normal distribution centered around the true population parameter, in this case a beta 1. Now when we add more predictors, this still stands with each of our parameters. So we could do the same thing for this case, beta 3. So if we sum up all our beta 3 estimates from all our samples, and we divide by the number of samples that we took, this number will approach the true population parameter of beta 3. And will form a normal distribution around this parameter estimate. So that's why we can still take t-tests and still form confidence intervals around each of our parameters. T-test. So if we wanted to solve for the t-test of a numeric predictor, so in this case age, it would follow the exact same format that it did in simple linear regression. So we would take our coefficient estimate minus our hypothesized value, which in this case is 0 because we're proven statistically significant, and then divided by our standard error, which here is 4, and we get a value of 0.5. So we'll reject if the absolute value of our t-score, or 0.5, is greater than our critical value. So our critical value, we're going to use degrees of freedom is equal to n minus p minus 1. So we see that we have 20 observations, and then minus the number of predictors, which in this case we have 2, and then minus our intercept term to get 17. And then our alpha value is going to be 0.05, and since it's a two-tailed test, divided by 2 to get 0.025. So now we can look it up in our t-table, and you see here it's 2.1098. So we see that this number is less than our critical value, so we fail to reject. So it's not a good predictor. Now we can find the t-score of a categorical variable. So the format's going to be the exact same, just the hypothesis is going to be slightly different. So in this case, we have, it could be male or female, and female will be in the baseline. So female is added to the intercept term. So our null hypothesis is still going to be, in this case it's beta 2, value is equal to 0. But what this is saying is that the salary for men is no different from the salary from females. And then our alternative hypothesis is going to be beta 2 is not equal to 0, or that the salary of males is different from the salary of females. So here we have our parameter estimate is going to be 5, our hypothesized value 2, and then divided by our standard error 2, and we're going to get a value of 2.5. So we're going to reject if the absolute value of 2.5 is greater than our critical value. So our critical value, we're just going to use degrees of freedom is equal to n minus p minus 1, so 20 minus 2 predictors, minus our intercept, we get 17, and then our alpha values is going to be 0.05 over 2. So if we find this on the table, 17.025, we get 2.1098. So since our t-score is greater than our critical value, we're going to reject. So what this is saying is, at a 95% confidence, and holding our age parameter constant, we can say that the salary for men is different from women. Now what if instead we wanted to form the hypothesis that the salary for men is greater than women? So you could do the exact same thing, you would just do a one-tailed test. So the only thing that would really change is the critical value, because you're using one tail instead of two. Confidence intervals. So just like how t-scores behave the exact same way for simple linear regression and multiple linear regression, so do the confidence intervals. So say we want to form a confidence interval for our beta 3 parameter, or masters. So masters is part of a categorical variable education that's 3 levels: high school, college, or masters. So the confidence interval formula is still going to be our beta parameter plus or minus, and then our t-score, and then times our standard error. So we're already given our coefficient estimate, which is 8, plus or minus, and we're already given our standard error, which is 5. So we just have to find our t-score value. So it's going to be alpha over 2, and then degrees of freedom is equal to our m minus p minus 1, which is 28 minus 1, 2, 3 predictors minus 1, so 24.05. So we go to our chart, we can see that the t-score is 1.7109. So we plug in and solve, and we get a confidence interval of negative 0.5545 to 16.55. So what this is saying is that in the population, the salary of someone with a master's is between negative 0.5545 and 16.55 greater than the salary of someone in high school, or the baseline estimate, which you can also gather is not statistically significant because it has the value 0. F-test. So F-test we didn't learn in simple linear regression. So what an F-test does, it decides whether any of the predictors are statistically significant. So here we have 4 predictors: beta 1, beta 2, beta 3, beta 4. So if we reject our F-test, it's saying that at least one of our beta parameters is statistically significant. If we fail to reject, it's saying none of them are significant, and we should just keep the null model, or intercept value of 4. So our null hypothesis is going to be that our beta 1 value is equal to our beta 2 value, is equal to our beta 3 value, is equal to our beta 4 value, which is equal to 0. And then our alternative hypothesis is going to be that at least one of our coefficient estimates is not 0. So the formula for this is going to be F statistic is equal to total sum of squares minus the sum of squares error divided by p over our sum of squares error divided by n minus p minus 1. And this is also equal to our MSR over our MSE. So we already learned what MSE is, which is our SSE over our n minus p minus 1. or our unexplained variability divided by our degrees of freedom. Now our MSR is going to be equal to our explained variability over P. So this can be thought of the amount of variability explained per predictor. So the values an F-test can get is going to be anywhere from the value of 1 upwards. 1 would mean the least significant, higher values mean the most significant. So your goal is to get high values for an F-test, because that means it's extremely likely that you have at least one significant predictor. Okay, so here we have the example of 4 plus 5x1 plus 8x2 minus 3x3 minus 1x4. So our null hypothesis is going to be that all these values, coefficient values, is equal to 0. And then our alternative hypothesis is that at least 1 is not equal to 0. So if we want to solve for this, we can first solve for our MSR. So our MSR is equal to SSR over P. And then our SSR value is given to us as 120. And then P, or our number of predictors, is just going to be 1, 2, 3, 4 to get a value of 30. I'm solving for our MSE. We can solve for our SSE as our total sum of squares minus our explained variability, or SSR, to get SSE, and they're divided by n minus p minus 1. So n is 25, minus p, which we found to be 4, minus 1. So we get 80 over 20. So we plug in 30 over our 4, and we're going to get a value of 7.5 for our F-test. So on the exam, we're not given F-tables, so in order for you to test whether or not it'd be significant, they'd have to give you the value, such as if the critical value was 8 per se, then it'd be fail to reject, because this number needs to be greater than the critical value. And then if the critical value was 6, then we would reject, and we say at least one is significantly, at least one of the predictors is significant. Partial F-test. So far we learned how to test if individual predictors are statistically significant and if any of the predictors are significant. But now we're going to learn how to find if a subset of predictors are statistically significant. So say if we wanted to find if the education variable as a whole was statistically significant. So we couldn't do this before with a t-test because that would simply examine one of the possible levels to the baseline, which in this case would be high school. But if we wanted to find if it was education as a whole was statistically significant, we'd have to take both these predictors. So if we set our null hypothesis, it's going to be that beta 2 is equal to beta 3, which is equal to 0, or a null hypothesis, which is going to be at least 1 of beta 2 or beta 3 does not equal 0. So the formula we're going to use to do this is going to be the sum of squared errors of our partial model minus the sum of squared errors of our full model divided by predictors of our full model minus the number of predictors of our partial model all over sum of squared errors of our full model over n minus the number of predictors of our full model minus 1. So our partial model is just going to be the model without the predictors that we're trying to test for. So our partial is going to be run speed is equal to 12 plus 1 times our height. And then our full model is just with all the predictors. So we're given our n value, we're given the sum of squared errors of our full model and our partial model. So now we just have to plug in. the sum of squared errors of our partial model minus our full, divided by the predictors of our full model. So we can see here it's 1, 2, 3. And then minus the number of predictors of our partial model, it's just 1. Then over the sum of squared errors of our full model, over n, just 20, minus the predictors of our full model, which is 3, and then minus 1. So we can plug in, and we're going to end up with 50 over 12.5, and we're going to get a value of 4. So just like with our f-test, higher values means more likely to be statistically significant. So we're going to do one more example of a partial f-test. So our formula again is going to be sum of squared errors of our partial model minus the sum of squared errors of our full model, divided by the number of predictors of our full model minus the number of predictors of our partial model, divided by the sum of squared errors of our full model, divided by n minus the predictors of our full model minus 1. Okay, so say this time we only want to do one predictor, so we just want to do x2. So in this case, it's going to lead to a special example that we can use. So first we're going to plug in and solve for our values. So we're going to get 200 minus 150 divided by the predictor difference. So that means our partial model is going to be only y is equal to 10 plus 2x1. So our full is going to have 2 predictors, our partial is going to have 1. So 2 minus 1 divided by the sum of squared errors of our full. 17 observations minus predictors of our full minus 1. So it's going to produce a value of 5. So a special rule is that when you only use one predictor for your partial f-test, this partial f-test, or 5, is going to be equal to the value of our t-score squared. So if we take the square root of 5, we can find that our t-value is going to be 2.236. So now you can use this value, and just like a regular t-test, you can find if the parameter is statistically significant using a t-table. So we're going to reject if 2.236, the absolute value, is greater than, and then our critical value. So let's say we're using alpha is equal to 0.05. So it'll still be 0.05 over 2. And then for degrees of freedom, it's going to be n minus p. So it's going to use the predictors of our full model, which is 2, and then minus 1, which is going to be 14, and then 0.025, which will produce a value of 2.1448. So since it's greater, we can reject the null hypothesis and say that our predictor x2 is statistically significant. But you can only do that when you're using a partial f-test on one predictor. If you try to use it on more than one, then that rule no longer applies. Problems with r-squared. So we learned in simple linear regression that you can use r-squared and residual standard error to judge the performance of your model. But now we're going to learn what can go wrong with using r-squared in multiple linear regression. So, as you add more predictors, it'll cause your flexibility to increase. So no matter what predictors you add, your flexibility will always increase. So as your flexibility increases, it'll cause your sum of squared errors, or the amount of unexplained variability, to decrease in your trained data. So if you're judging your r-squared from your trained data, as the flexibility increases, or as you add more predictors, the sum of squared errors will decrease, and then your SSR, or the explained variability, will increase. And we learned that r-squared is equal to our sum of squared errors over SST. So if you just keep adding predictors, no matter what they are, you'll keep achieving a higher and higher R-squared value. So obviously it's not a good metric then to represent how well the model is performing, because if you add bad predictors, your model is not going to perform very well. So the second problem. So when you run a multiple linear regression, the most predictors that you can have is n-1. So if you have 50 observations, the most possible predictors that you can have is 49. If you had 100 observations, the most predictors you can have is 99. Now, if you use, say, 99 predictors for your 100 observations, your R-squared value would equal to 1. Or you would guess every observation perfectly in your train data. So the other problem with R-squared is you can't have a large number of predictors compared to observations. Because whenever you do have a lot of predictors to observations, so a high P to low N, you will get a high R-squared value, or an inflated R-squared value. Okay. So that wraps up this section. Next section we're going to learn feature selection techniques, because the problems with just finding whether individual variables are statistically significant or not, and then dropping if they are or not, for instance 95% significance, we're going to be wrong 5% of the time. So if you have 100 predictors, you're going to end up dropping or keeping 5 of the variables you don't want. So next section we're going to learn how to perform feature selection more as a whole and produce the best results on the test set instead of just taking individual predictors at a time. So I'll see you all for that. Thanks.